So this is a little personal project that I've been trying to work on. I was hoping to have it finished for this conference, and I've hit a couple of tricky little issues. So I'm going to present where I've got to, and then hopefully all you guys can then suggest what the next step is to fix the thing. I was hoping Jim was still around, because I think Jim probably knows why it is the way it is, but anyway, we go through. So some of you may know there was an overhead projector option for the 39G and the 49G calculators. So these are the ones with the rubber keys and the frozen hamster butt colour, as it was famously described once. And what it is an external LCD screen. It's about 5 inches, maybe a bit less, by 3.5 inches in a surround, and you stick it on top of a traditional overhead projector, and I'm sure I don't need to tell you all what one of those looks like. And you can plug the calculator into it, and it mirrors the display onto this second screen, and then clearly the projector projects that. So if you're a teacher, it's great. You can then show the whole class what's on your calculator. So nice idea. There's a few of them knocking around on eBay. You occasionally get them. This picture is from the conference thumb drive. But no, the 50 does something slightly different, and we can come to that at the end if you want. There's also there's a card that will go in a 48SX, and then the cable does the same thing. So what is the project? So I thought it'd be a good idea if I could build something that would take the signal coming out of the calculator and display it on a PC or an HDMI screen, so that you can ditch the projector. No one has the old style projectors anymore. Wouldn't it be nice? And for our conferences, you know, it'd be lovely to have a big screen projected.
One quick question. I remember back in the days when we did conferences and we had this problem, 20 years ago, whenever it was, and I bought for the conference an overhead projector, which I have on the shelf at home. One of the problems is that there are basically 2 types of these overhead projectors. One of them has a special, I guess, glass on top that's designed so that what's sitting on top of it doesn't get hot. If you put the calculator on there, and the old-fashioned ones, it almost end up boiling the calculator.
Yes. Yeah, so I think what Richard is saying, so there were 2 types of overhead projector, the reflective ones and the pass-through ones that needed an acetate. So this is designed for those pass-through type projectors, but they did get very hot because you had that big bulb underneath and so on. So this is the thing in slightly more detail. There is at the bottom here a socket, and that's like an 8-pin mini DIN type cable goes in that end. I've got the pictures of the cable coming up. There is a thumb wheel to adjust the contrast, and then that clicker button is a rocker. It goes up or down, and what that does is move the display up 1 line of pixels at a time or down. And the reason for that is there are not enough wires in the cable to have an end of display signal. So usually it works fine. If you turn the calculator on, it sort of works, but sometimes if you turn the display off and then on again, it gets confused, and you end up with a screen half wrapped around, and you have to click it a few times to bring it back up to the top again. Excuse me. So it's quite a nice thing. I took mine apart. It comes with, there's a 9-volt battery inside for when you're using the SX card, the 48SX. You don't need the battery for the 49G. It seems to be able to generate enough voltage to put a contrast onto the display. But it does actually not work if you have the battery in. And I didn't take it all apart, so I've only got the picture of the back of the board, but there's a pretty meaty board in there for driving an LCD display, frankly. So at some point, I'll have to take it apart a bit more and see what's on the other side of it. But to get the back off there, it's just ordinary Phillips screws, so I didn't want to go any further in case I broke the thing. And there's a bit of, let's see if I can make this work. There's a bit of wrinkle here. That's just the plastic protective cover, so I've never bothered to take the plastic cover off the screen. So on the cable, this is a couple of yards long. The end that goes into, can you actually see that on this display? So on mine you can see
Inside.
there's little pins there. So this is about a couple of yards long.
There you go.
Oh, that's much better, thank you. This is an 8-pin mini DIN, and then this goes into the calculator. So this is a custom 10-pin connector, and you have to be very careful with these. So if you read Joe's page, on the bottom here you can't quite see, there is a key way to fit it into the back of the calculator. You have to be very careful to use the one with the dome-shaped keyway. There's another one with more of a ridge, and if you use that it all goes horribly wrong because the wires are wired up differently. So how to approach the problem? So I first started off with the idea of using a Raspberry Pi. Everybody says, use a Raspberry Pi, they're lovely. And it seems like a good candidate because it's nice, small, self-contained. It's got HDMI output, and clearly it's got the I/O pins for receiving the signal. But I discovered that quite quickly, to be honest, it was very good for slow things like controlling a switch or turning on an LED in working at human speed. And you can use a bit of Python and it's lovely. The moment you want to do something faster and you need a bit of C and you need to run much nearer the bare metal, it becomes a real problem. So Linux has no real-time process priority, whereas old-style Unix does, which you can use at great peril, really. I've done it before, and it's quite easy to lock up a machine and you have to restart everything, but there we go. So the way to do it in Linux would probably be to write a device driver. For me, that's quite a big learning curve. I did have a look, and there were lower drivers and upper drivers, and it was completely unlike any Unix device driver I'd written before. So I thought, I'll give up on that. And if you go to the bare metal itself, well, you've then got a full computer to initialize, and you end up rewriting most of the operating system if you want to initialize the HDMI subsystem and initialize other bits and bobs that may or may not cause a problem. So I kind of stopped on that idea. I did have an idea for a no soldering solution, so it's not quite no soldering, but I thought one of those cheap, no-name, Chinese-made parallel to USB port connectors might just do the trick. You could put the data lines onto some of the pins, you could put there's an X clock that tells you when there's a bit of data available, and I thought you could put that onto the DTE, I think it's the data terminal enable or data select, I forget which pin, and essentially every time there was some data to be read, the USB would receive it and you'd get ASCII characters at your end, and then you could reverse interpret those and see what the bit pattern was, and it would be there. And avoids the device driver issue because it's now just a USB serial from the computer's point of view. And it's all lovely except, well, I don't know if it's lovely because I didn't actually try it. It may not have worked. The calculator may have sent the data too quickly. But the catch is that the data ready signal is an active low signal in the parallel port world. So that means we need a bit of logic gate to negate that signal. And if you're going to solder on a small logic chip or create one with some transistors, it's completely defeated the no soldering part of the solution. So that's on the back burner, and I probably won't do anything with it. But I'd like to produce something that is really easy for people to copy and recreate. So the next and where I am at the moment is an Arduino. So Some of the modern Arduinos are extremely fast, so they're more than capable of handling the speed at which the calculator's sending these signals. So you've got plenty of I/O pins and you've got USB. So the idea would be to set up some interrupts, receive the pixel data as it comes through, build that up as an internal bitmap in memory, and then have a second process running in parallel on a different timer trigger to send that bitmap over the USB port to a PC. And that can be done much more slowly, 5 or even 2 frames a second. In fact, Joey had exactly the same conclusion in his presentation, I noticed. And I think that would work fine. And again, because it's USB, it's just a serial port from the PC side of things, so writing the software there and displaying it on the screen is relatively straightforward. It's not trivial, but it's there. So what do the signals actually look like? So there are some port pinouts. I got this little diagram off the internet, and amazingly there's some bloke called James Donnelly I should thank for this information, so thank you very much, Jim. I won't go into too much on this side. I did get myself very confused because this is looking at the calculator, whereas I was looking at the cable a lot of the time, so you have to really be careful where you are. But the 10 pins, so the first 4 are the serial ports. So I don't, for those who have forgotten or don't remember, the 48 has a serial option, and that was carried through into the 48G plus whatever it is. But they added 6 more pins. And here, so these are roughly, as best as I can work out, I'll start from the bottom up. I'll start from the top and the bottom. There's a ground, which is, if that's a nominal 0 volts, then there's a VCO, which is at +5 with respect to this. And then LD0 and 1 are pixel data pins. So as each pixel is written, that value is either high or low for pixel on or off. And the reason there are 2 of them is because the screen is driven in 2 halves. So the graphic display does half of the screen, and then the second pin does the other half. So when you're scanning across, it comes from 1, and simultaneously, so you get pixels across the width, they're 128, so you get 0 to 63, and then 64 to 127 come simultaneously. So you get 0 and 64, then 1 and 65, and so on as the thing comes across. What's slightly odd, so these are at the positive is 9.5 volts with respect to ground, or 0 is 5 volts with respect to ground, which is a bit confusing. So this VCO is the more traditional ground for these. So if you consider that to be 0, then these are between 0 and 5 volts. And then it kind of makes a bit more sense there. But it is a bit odd to start with when you're reading these things. So I'm not quite sure why that was done, and maybe Jim will be able to tell us afterwards. But it does mean that you've run out of pins. So here's 2 for the data. This, I presume it means X scale, but I don't know. But this is a clock pulse for going across, so 64, 2 lots of 64 sets of data. So bang, 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 and every time it goes bang, you read the LD0, LD1 to see whether the pixel should be off or on. When it gets to the end of the line, the LP signal fires, and you get 1 positive to say, I've reached the end of the line, and then you wrap around. And what's missing is the end of display. So when you've got to the bottom of the display, hence the little micro switch on the overhead projector itself in order to resynchronize when it loses its sync. So here are, sorry, just fell off the chair. So here is some oscilloscope pictures, screen dumps. So the first one up here is, I should say at this point, I changed the way I was capturing the signals. So I originally started with some pins, and I thought I'd put some pictures in of that. I must have lost them on the display, on the presentation somewhere. Sorry, this is what comes of doing it very hastily. I started off by, I found on the internet a company that sells a 10-pin connector block that is the same spacing and pin size as the socket in the calculator, and then I wired those up to breadboard pins to plug in and tap into those. Because of the funny things that are happening, that I'm going to come to in a minute, I then decided, well, maybe I made a mistake with that. So what I've actually done is I've taken the original cable, and I'm not going to cut the original cable, so I got a bit of Ethernet cable and just wired two 8-pin mini DINs on each end. So what happens now is I use the official cable from the calculator into mine. I've then split it out so I can put the oscilloscope probes onto the bare wires and tap the voltage levels, and then carries on to another 8-pin mini DIN that's actually plugged into the overhead projector. So because I'm using a bit of Cat5 cable, you can see there's quite a lot of crosstalk here. So this is the LP, the line, the end of line signal. So you can see here, there's end of line, there's some data coming, which is this crosstalk, and there's another end of line, there's a bit more crosstalk, and then on the X scale, this is, you can see there's a bang, 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 and then bang, 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 bang. So there's a signal, there's a delay of a few, it's into a couple of milliseconds. I'd have to go and work it out on the thing. So the scale here is 25 microseconds per division. Oh, it's in the microseconds thing. Down here is the same thing zoomed in, because the oscilloscope has this lovely zoom in thing. So here is the initial peak, and then you can see the clock trace here, and it looks much more regular. This looks a bit irregular, and it's just an artifact of the lack of resolution on the oscilloscope screen. So you zoom in and you see here there's quite a nice sawtooth wave. So all's looking so good, apart from that bit there, which we're going to come back to. Just for interest, so here's the pixel data against the end of the line. Again, here's the thing, and here are some pixel values. So on this bit of screen, there's a couple of pixels set, and then nothing set, and then one at the end. And the scale here is 2 volts. Well, they're both 2 volts, so you're saying we're getting about 4 volts. This one is going up to 4.5. So it's kind of what we're expecting, and it's looking all right at the moment. And the 0 is a 0, so that's all looking good. And then here's just another bit of data further along. So this is just a different bit of screen. But interestingly, there are some 0.7 volt type values here. I'm not quite sure what that is yet, but I haven't got far enough to know whether that's going to be another problem. So the voltage challenge, as I'm calling it, there's a big gap here. So the low for the X scale, and it's only the X scale, so it could, you know, I presume it's the same on every calculator. I haven't tried a different one. Starts at about 0.7 volts, maybe a bit less, 0.6. And the problem with that is it's above the low threshold for an Arduino. So if you want the Arduino to say trigger on low, it will never trigger because that's too high. And I've scoured the internet looking for voltage converters or signal cleaners or whatever you want, you know, a bit of chip that might bring that down to a smaller level, or a voltage converter that has a higher threshold. Yes, Eric?
74 HCT 240 octal or 244 octal buffer that has Schmidt trigger inputs.
Okay, that might be my answer. Yeah, indeed. So one thing I tried was a voltage divider, and that struck me as a very strange result. I mean, I just picked some resistor values of ones that I had, so they were 11K, something like that, for the top bit. This bit has stayed the same, but it has divided this bit. So I don't know, I'm guessing that there's something in the calculator that is trying to keep that level at that level for whatever reason, and I've no idea why. I've no idea why. So that's the end of it. And if someone can elaborate a bit more as to why that might be happening, or a suggestion, and I've got one from Eric, thank you very much, that would be most interesting. Tom?
Does the ground of the display have to be connected to the ground of the calculator? I mean, since it was designed to connect to the calculator, that doesn't seem to make much sense, but there just seems to be a reference issue here.
I agree. So Tom's comment was, does the ground of the display have to be connected to the ground of the calculator? Well, there were two grounds, and both of those pins are carried through. So yes, it is. So I'm tapping into the cable. I've effectively split the cable. So I don't think I've changed anything. While this happens, by the way, the display works fine. It all, the overhead projector display is all working fine. And I did try putting a battery in backwards to try and subtract 1.5 volts out of that. And admittedly, I was only just squeezing it with my fingers. I didn't do a terribly efficient job, but the calculator display started going haywire at that point, so I didn't pursue that any further, which is why I think there's an element of the calculator is trying to maintain that ground, that level. The answer to why is there a 9.5 volt in there, and I think that's probably linked to why there's a battery in the overhead projector. I have tried it with the battery and it doesn't change these. If I remember right, it doesn't change this.
Who made it?
This is the official HP one. I don't know who actually made the
You
thing
can't track
itself.
down technical information on it,
There's very little out there, not at the electrical level. There's very little anyway. But,
There was a little bit of discussion on that many years ago in ComSys HP48, and I was just actually trying to Google it and track it down, and I was not able to, but I don't think even at that time there was enough detail that would help you with this.
So I had one last idea. In fact, I was talking to Joey yesterday, and the act of talking to people is wonderful for generating ideas. And I thought I might be able to trigger on the down signal. So as oops, from one end, just go back. So, I lost the button, there we go. So this might be too low to trigger as low, but as that comes down, it's just possible the Arduino's trigger on the falling edge may trigger, because the falling edge may only have to get into the no man's land between low and high, as opposed to get all the way to low before it triggers. So I need to just maybe write a bit of code to experiment with that, but that might just solve the problem. But the thing is perhaps slightly frustrating, if I go forward, I think is that the LD0 and the LD1 pins are fine. They have a base, a 0 is 0, so there's going to be no problem reading those, or no problem other than making the thing work, the usual one. So it's just this one clock signal, one clock line that has this strange figure. Dave.
Looking at the LD and L1, it's such a narrow signal that I think you will have to figure off the transition rather than the level.
Yeah, so the suggestion, the recommendation was the signal was so narrow that the Arduino would have to be set to interrupt off not the level itself, but the transition. So the change from up to down, or the change from where it was to down. Yeah. So something to try, but I'll speak to Eric afterwards. So I'll finish up now, and thank you very much. And then hopefully hopefully next time I'll be able to bring a working gadget, and then all I have to do is get past airport security explaining how this thing works without them demanding that I have an overhead projector set up. Thank you.